I'm going to talk about the connection between finding areas under curves and antiderivatives and how they're related. But first, I got to lay a little bit of groundwork. We're going to understand a couple things. Suppose we're interested in the problem of finding the area underneath the curve, general curve, f of x. Okay, one way. So we want this shaded area here between the curve and the x-axis. One way that we could approximate this. Now remember, this is just a theoretical thing. All right. One way that we could approximate this is to start out by partitioning the x-axis. We'll call it, here's A and here's B. We're going to partition the x-axis into any number of pieces that you want. All right. And what we're going to do is, all right. So partitioning the axis also partitions up our region into these strips. And what we're going to do is we're going to add up the area. We're going to ballpark the areas of these strips, and then we're going to add them all up and say that the areas of the sum of the areas of the strips will be approximately equal to the area of the entire region. So this is how it goes. We have several subintervals here. Call that delta x1. And this is the second one here, we'll call that delta x2, and so on and so on. The general one will be, I write delta xk, and the last one will be delta xn. So we're assuming here that we have cut this thing into n different strips. So what we're going to do is pretend that these are the widths of these rectangular sort of shaped strips here. So this is like width 1 and width 2, width k, width n. And what we're going to do is, let me do one specific one right here. Suppose that the function looks something like this. And here is a subinterval. So we'll say that this is, suppose that this is just one of these in here. Alright, so this one will be, say, delta x sub k, just a general one, the kth one. What we're going to do is we're going to pick an x value inside here. Doesn't matter really where it is. We could try to get it right, so maybe pick it to be like this one here, and we'll call that value x k star. X sub k because it's in the kth subinterval, and star because it's more or less arbitrarily chosen. So what we're going to do is f of x k star, f of this number, f of this x value, is this height here. So it gives you this, and we draw it with a dashed line. It gives you that distance. So we could make a rectangle out of this, like so. And let me just highlight that. So the actual area is the area under the curve. Alright, the area of this region with the curvy top. But we can ballpark it this way by choosing a width, right? We got this, and we're ballparking it. Now, I could have chosen this better or worse, right? Like, it appears that this particular rectangle is an underestimate of the actual area that we're looking for, because this space, according to how I have it drawn, has a greater area than this space here. So right, like this is more than this. So this is like an underestimate. Now I could fix that by tweaking the value of xk star that I chose. It looks like if I chose it just to the right a little bit, the rectangle would have had a slightly different height, and it would have been a better estimate. Now we don't have to worry about that too much right now. I just need you to understand the process that's at work here. So what we're going to do is we're going to take something that's like that. Let me just get back in here. Okay. And we're going to make these strips. So we're going to choose an x value inside each one of these. I'm just going to write it down. I'm not going to write every single one down because you get the idea. And that'll be one rectangle, two rectangles, and maybe we'll have 3, 4. Remember, we're choosing an x star from every one of these things, trying to get our best estimate here. Here, here, and here. Now, this is the areas of these rectangular strips is something that you can actually find, right? Because you know what f of x is, you know how to calculate all of these heights. So And we know what all these other numbers are here. So let's suppose that this was, say, 1 and this was 11. And we decided to cut this thing into, say, 10 strips. Alright, so we would have delta x 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we would have 10 subintervals, we would pick 10 xk stars, and we would get 10 heights out of these. And we would add those all up, and that would be an approximation of the actual area. We can get this actually pretty good, depending on how we choose the x stars, right? You saw with this thing here, if we really paid attention and tweaked every single one of these, we could get a really good approximation. Well, approximations are nice, but we want the actual thing. Now, unfortunately, before we get into that, you got to finish off this video, and the conclusion is going to come at the end of the response to this. But the idea here, to get the exact area, it should be clear that the more rectangles we use, the better the accuracy is going to be. So, like right here, this is a wide subinterval. If I were to say cut this thing in half and try this game again, right? Say that instead of going all the way here, I went just this far. Now, if I pick a different, see, I'm just concentrating on this thing here. If I try it again, right? If I pick xk star to be this guy here, we'll probably get a better estimate of what that smaller area is, and it's going to cut down on the error. So one of the ideas that you have to buy is that the more of these things that we use, the better the approximation is going to be. Let me write this out in sigma notation here. I'll just go Y for a sec. All right. What we have is the area is approximately equal to, now what's this going to be? We're going to be adding up the areas of these rectangles. So I'll call this, say, R1 and R2, and this one will be R sub k, all the way up to R sub n. So the area of the first rectangle will be delta x1, right, for the base, times the height, and that'll be f of x1 star, right? It's base times height. Plus, this is R1, and then R2 is f of x2 star times delta x2, and so on and so on. Now let me write this in sigma notation. I want to clean this up a bit. We have the area is approximately equal to, we would continue this all the way up to f of xn star times delta xn, but the area is approximately equal to the sum of f of xk star delta xk from k equals 1 to n. Alright, so it's just an approximation, and we should understand that the larger n is, the better the approximation we get. Now, this is where it's going to get a little bit theoretical. Okay, we're going to define the area underneath such a curve. We're going to define the area by what it would be if we could take a sum, if we could use infinitely many rectangles for this. In other words, the actual area would equal what we would get if we could take the limit as delta x max approaches 0 of this 1 to n, f of xk star delta xk. Okay, it's a theoretical definition. All right, it's a big if. Okay, if we could somehow, now wait. First, I gotta tell you what delta x max is. When I carved this region up, I was non-specific about how I made these delta x's, the 1s, 2s, and 3s, just because of how I have it drawn. You might assume that they all have to be the same width, but they don't. All that we want to say here is, if, it's a big if there were some way that we could take this region and increase the number of subintervals that we use, thereby increasing the number of rectangles that we're going to be using. If we could increase it in such a way that the width of the largest one, wherever that may be, goes to 0, then the resulting number would be what the area is. So kind of think of it this way. Think of going from something that could start like, say that we want this area here, from here to here. If we use one rectangle, right, we're probably not going to get a very good approximation, right? But if we use millions and millions and millions of them, if we try to fill this space as much as we can with these rectangular strips by making our delta x's really, really tiny, okay? If we could figure out some way to do this process over and over and over again, to use infinitely many rectangles, we would fill this entire space, and that would be the actual area. That's how we're going to define what the actual area is. Now, this gets its own special symbol, all right? If we have some kind of a sum that's like this, which is just base times height, base times height, base times height over and over and over again, the theory goes, if we could figure out a way to drive this to infinity, right, n would go to infinity, and the width of the largest subinterval, delta x max, would go to 0, so that shrinks down to nothing. This gets its own special symbol associated with it, and that's this. Alright, from A to B of f of x with a dx tacked on to the end. Okay, this symbol is what you would get, or the definition of this notation is this limit. This signifies a limit. Okay, anything that looks like this, if you could take the limit as delta x max approaches 0, thereby using infinitely many rectangles and filling the entire space, right? Such an expression would mean that's what this means. Okay, so when you see this symbol, one way to look at it is to remember that it comes out of this. Okay, this is where the action is. It's all about this idea here with the limit, of course. So this is really just like a neat sort of way to wrap this whole process up. When you see this, you should think the limit of a bunch of strips of areas as the width of each one approaches 0, and thereby filling the entire thing. So this is another fancy way of saying the area under a curve, the net signed area, I should say, under a curve from A to B, but it really comes out of this. Alright, also, the reason why I say net signed area is, suppose we did that with a function that looked like this. Let's say we have this thing here. Okay, so here's A, make that at 0, and here's B. If we play this game with rectangles, which means we're going to carve this region up into a bunch of, alright, cut it up into a bunch of different pieces here. So it'll be, let me try to zoom in here a bit more here so we can see. Okay, this first one is delta x1, delta x2, delta x3, etc., 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 delta xn. Alright, when we cut this up, it implies a partition of our region. I'll save that one for a second. Alright. And now, remember, back here, right, when we first started doing this, I just said that it was going to be f of x 1 star, delta x1, f of x2 star, delta x2. So if the value of f is negative, then the quote-unquote area of the rectangle gets counted as a negative quantity, right? It's going to get counted as a negative quantity because the f part is going to be negative. Now this gets counted as something that's positive, so we would pick an xk star, an x1 star in there, get this area. x2 star, get that area. x3 star, maybe get that area. Now this one here is going to be maybe like this. Alright, what's going to happen is it's going to end up looking like this. And the way that that's going to show itself is when you, if you were to do something like this with a function that goes negative sometimes, what's going to happen is the areas, I use the term loosely, are going to cancel. If you did this process for this function just on this piece here without this negative stuff, you would get the area. Alright, that it would stand for the actual area. But if you did it from, say, here to here, you would get a number that was the opposite of the area. So suppose that the area is here. Let me write this down in a different color. Suppose that we know in advance that the area of this section here is 2, and suppose we know in advance that the area of this section here is 5. If we did this kind of process with this function here from A all the way up to B, so across this negative region here, the answer that you would get would be -3, because this piece would give you 2 and this piece would give you -5. So they would have to add, because we didn't really distinguish between positive and negative values here. We just said that the rectangles had height f of x k star. So if the height is negative, then the quantity gets counted as a negative number. Now that might seem something that's a little bit weird to talk about in this context of area, but it does actually have a very good use. And we'll talk about that in the upcoming video. So the one last, I just want to repeat this again, and then we'll get into one more thing, and then we should be ready to see it. We have the approximation of the area of something, right? We got, I'll just recap this again. Let me see here. So we have, whoa, okay. So we want the area under some curve. So what we do is, theoretically, we could carve it up, A to B, into a bunch of these different regions. So we partition the axis, and we make rectangles out of these pieces here by choosing, how do we choose the height of the rectangles? We choose them more or less, we would try to pick a nice one to make it work out nice. Like clearly this one is an overestimate of this strip here. But as we use more and more of them, it's going to matter less and less the ones that we pick. So we're going to say that the area, so the approximate area equals the sum of f of x k star delta x k from k is 1 to n. Alright, so that's just the approximate area. And if we could do this process over and over forever and ever and ever, alright, if we could, it's a big if, but the idea, the concept is really just as important. Alright, think about, I mean, it seems like it's useless because it's something that we really can't actually do this forever, but it's still useful to understand the concept. If we could, how would we symbolize it, right? We fill this entire area here. So if we could, that would mean taking the limit as delta x max approaches 0 of such a sum 1 to n of f of x k star delta x k. Such a limit gets its own special notation, and what we know to be a definite integral we call. And it gets this as s for sum from A to B, depending on where we're starting and ending. And we drop the k and the star, and we just write f of x referring to the function, and delta xk gets dropped and replaced with dx. So when you see this, always keep in the back of your mind that this is where it comes from. This is where the action is. This is what's really important. Now, before we go on to the next video, I'm going to bring up one more thing that talks about the mean value theorem. If you understand the mean value theorem and how it applies to the fundamental theorem, then you can just stop watching now and go right to the next one. But I'm going to cover it here anyway. So the mean value theorem says, okay, the mean here, where are we? The mean value theorem says, typically this is how it's taught. If you got some function, let me go wide here. If you have some function that's continuous on some closed interval, so let's say here's A and here's B. All right. If the function is continuous and differentiable, I'm sorry, it has to be differentiable. The mean value theorem says that if you take the slope of the, say that this is f of x here, of course the function is f, the slope of this line, we define that as the average rate of change of f from x equals a to x equals b. The mean value, and the slope of that line is, we write it as f of b minus f of a, the same thing that you've been doing in algebra for years and years, b minus a, right? It says that that slope, it says that the derivative of this function at some point in between a and b must equal that slope, right? So it's about derivative. So the derivative of this function at some point, at some value of x inside here, must equal the slope of this line. Now, where is that going to be? You can sort of see this right away if you know what you're talking about. If I say pick this value of x here, say this x value, this is not the correct value because the slope, the derivative there, is different from this slope, right? So the value that it's going to be at is going to be about right here on the curve. The mean value theorem guarantees the existence of one such point. I'm going to call that x star, right? It says that this equation, f prime, the derivative of the function, evaluated right, at x star. It says that there's guaranteed to be some x value inside here, such that this equation is true, such that the instantaneous rate of change, which is the slope of the tangent line, is equal to the average rate of change, or another word for average is mean. So the instantaneous rate of change equals the average rate of change, and that's what the mean value theorem says. So it guarantees at least one. Now, just let me do a couple examples of this just to let you know what I'm talking about and make sure we're on the same page here. So if I take something like this, there's a function there. I could say, typically these problems say find the value of x guaranteed to exist by the mean value theorem inside the interval here. Now, I'm not going to do this with any real calculation. I'm just going to point out that this is actually always possible. For this particular case here, it looks like there are two different answers. There's one value of x here, right, where the tangent is parallel to the secant, and there's another one as I have it drawn up here. Alright, so this one happens to have two values of x. So I guess I could call it x star 1 and x star 2. But the theorem guarantees the existence of at least one. But this doesn't really help us for what's going to... this is just the statement of the mean value theorem. This isn't going to help us in the next video. What's going to help us to understand what goes on in the upcoming video, so we can get a grip on the on antiderivatives as they apply to finding areas, is this. Instead of focusing on finding some number in here where the tangent line is parallel to the secant line, I'm going to rearrange this. I'm going to rearrange this formula right here, statement of the mean value theorem. I'm going to pull the, instead of writing b minus a here, right, for the length of here, I'm going to write that as delta x. Because that's really all it is, right? It's just a change in x values. This is a delta x, and really this is like a delta f. So another way to say this, a similar way to state this, is that delta f or delta y divided by delta x has to equal f prime of x star for some number inside the endpoints of this interval. So that's sort of a different way of looking at it, but the way that we are going to use it is this. We're going to I'm going to go back to the f of b minus f of a notation for a sec. So I'll say f of b minus f of a. What we're going to do with this is I'm going to multiply both sides by delta x and pull this over, so as to say that f of b minus f of a equals f prime of x star delta x. This is what we're going to use. This is the money shot. The restatement of the mean value theorem really says that the difference, right, a difference in a function can be written as the change in x multiplied by the derivative of that function at some point. And so what this is really saying is that changes in a function can be written in terms of that function's derivative and changes in x values. For example, let me see here. This is what we're really going to need for for this. Suppose we have a function here. Alright, all that this is really saying is that it looks like a more complicated way of looking at it, but it's really not. If you come back with this function here, alright, let's say we have this, and we have this, and this is f of x. Alright, it's all about changes. Okay, what this is saying is that this, if we make our little triangle here, this is delta f. Or another way to write it, you could write it as f of, if we call these a and b, we could call it f of b minus f of a, if we can see that, yeah. Another way to state the mean value theorem is that this change in f, alright, look, f is changing the entire time from a to b, right? It goes up and then it comes back down, but the total change is encapsulated by this positive number here. And what the mean value theorem says is that this green strip here can be written as, the delta f can be written as delta x, which is this length, I'll write it here, delta x, multiplied by the derivative of this function at some number inside here. And it happens to be the number that satisfies the mean value theorem. So let's call that one, if we call this value here, say x star, it means that delta f, this height, the height of this triangle, can be written as f prime of x star multiplied by delta x. So that the difference in f can be written as, can be traded in for this length multiplied by the slope. And that's what it is, right? This output here, what the height is going to be, the height is the slope times the change in x. That's just a regular formula from algebra, right? The change in height equals the slope times change in x. And the mean value theorem guarantees that f prime of some x value inside here will give you the correct slope. So that if you pick it to be the right one, the mean value theorem guarantees the existence of some number in here such that f prime of it gives you the correct slope, and that this can actually be done. Of course, if you choose the wrong value of x star, it's not going to work, right? For example, if in this case we chose x star to be, say, here, if we just naively assumed that it could have been anywhere and we went for it right here, which of these would have been larger? Delta f stays the same as delta f, but if we picked x to be this value here, the slope at this point is steeper than the slope we're trying to find. So that if we multiplied this slope, which is this, by this change in x, we would wind up with a much higher number. That's not what we want, though. Alright? And if we pick a smaller one, then we wind up getting a lesser one. So that's not what we want either. It guarantees that there's going to be some number in there that gets this just right. Now I'm going to do out one more example and do this one more time. So let me see if I can wrap this up in a way that actually makes some sense here. Here's the function, or here's the axis. If we got, say, this, and always draw the same picture. Here's A, here's B. All right. So the triangle piece here, we have the change in f is there. The change in x is the change in x. Right. So this is delta. Let me write it over here. Can I get that? All right. This is delta f, and and this here is delta x. Okay. So if we were to pick a number, say here, I'll call this x1. If we do f prime of x1 times delta x, so that means the slope at x1 here times this length is going to give us a large number, right? This is going to be greater than delta f, right? Because the slope is steeper. Otherwise, another way to look at it if we chose here, say x2. If we went with that one, we get that slope there. And from there, if we were to examine, let me just put a little barrier here, if we did f prime of x2 times delta x, we would be way off, because x2, I'm sorry, f prime of x2 is a negative number. So this negative number times this x actually gives us a loss, and that's going to be less than delta f. But the mean value theorem says that there's guaranteed to be at least one number in there that gets it just right. And for this case, it looks like it's right there. Right? And in that particular case, delta f can be, so that number is, we'll say it's here, and that's x star. So delta f can be written as f prime of x star times delta x. And we're going to use this fact when we figure out, when we start to talk about the fundamental theorem. It's going to be this is going to be crucial to our understanding of it. All right, the whole thing comes together with this little equation here, replacing changes in f with an expression involving f's derivative times a change in x.